Okay, let's get started. So the first course evaluation is over. We actually didn't get 90%, but there are two students. They don't show up. They didn't finish all the homework. I assume they probably will drop anyway. So I will give you guys the bonus points for that. Okay. Next week we're going to have the midterm and CTF. So like I said last time, to get prepared for this one, just maybe redo your homework, understand what's going on in your homework. So last week it seems like we had a lot of question in the homework. So there is a maze 2, which is not really the same as what we discussed in class. But that one maze 2 is supposed to be simple, even though it's not the same, but it's supposed to be simple. So what you need to do is you need to understand the disassembly 9 by 9. Try to think what it is doing. Okay. Do not just copy the share code we have in the class. Okay. So today we're talking about stack-based buffer overflow defense. This is our second class on this one. Then the second part of this class we will do some share code development. So we will write some share code together. Share code usually just I would say the one you are going to write probably 30 line of assembly anyway. But you need to know what 30 lines are those. Then if we have some time, we can start talking about format string vulnerability, but probably we will not have that time. So after the midterm, we will talk about format string vulnerability, ROP, also heap-based buffer overflow. So those three topics will be a little bit more difficult to understand than the topics we discussed so far, but they are also very, very interesting. So the second half of the class will move a little bit faster than what we do in the first half. The first half, I know usually it's very challenging for everyone at the beginning. The second half, if we have time, we'll also talk about cache sidechain. Okay. Anyway, we will start today's class with the canary bypass. We talked a little bit about this one last week. So today we're going to see a full demo, and as a homework, you are going to develop some script or program to generate exploits to bypass canaries on your machine. It's the same process for 32-bit and 64-bit. It's just 64-bit, you need to guess a little bit more. Anyway, everyone already know what the stack cookie or canaries are. They are just a random value placed usually in the compiler we're using. It will place that at a lower address than the saved EBP. So whenever you try to overwrite the content on the stack, you may, if it's a sequential overwrite. So far, we have been all the time we're doing the sequential overwrite. The format string vulnerability will be overwrite. We'll be able to overwrite arbitrary address. Right now it's sequential, starting from buffer sequentially to the higher address. So if you overwrite the stack cookie part, then when the function returns, you will check if those cookies have been changed. If changed, the program will just crash, showing stack smashing detected. So obviously, one way to defeat this kind of defense is to guess the value of the canary. Since it's 4 bytes, seems like it's very difficult to guess. However, we do not have to guess 4 bytes at the same time. We can guess 1 by 1. So then there will be just there are 4 bytes. Each byte we can guess 256 times. Then 4 of them we will just guess 1024 times. Then guaranteed we're going to crack it. However, the GCC we are using actually there is always a 0. There was always a byte. It's always 0. So we only need to guess 3 bytes, so which is 700 something, 768 times. So let's look at this vulnerable program again. This is a program I developed specifically for this class. It resembles all the web-facing programs where you have a parent process, and the parent process keeps creating child process. The difference is the program I created here is simpler. I'm not really receiving input from the web or internet. Instead, it is just reading a local file, try to open, the child will open that file. So on the right-hand side, you can see the main function. The main function is a big while loop. Inside this loop, we have a fork. And a fork is a system call. Of course, when you do it here, it's not really a system call, it's a libc function, but under the hood, eventually it's a system call. So fork is a system call that will make another copy of the running process. So whatever program calls the fork system call, it will create another copy of itself on the same operating system. So if you took OS class before, usually a very first programming assignment for you is to develop a shell. Just like the bash we have been using, actually on my computer I use Zeish. Also the virtual machine I gave you guys, I put Zeish there. So let's say if you type ls in your shell, you are trying to get the list of files in the current directory. So what happens under the hood is the shell program, it will first call fork system call to create another copy of itself. So there will be 2 copies of the shell program in the OS for a very short time. Then right after that, one of them, the child, will make another system call, the exe7e1, to replace the current process with the program ls. So for a very short time, there are 2 copies of a shell program there. After that, it's one shell, one ls. So there are 2 different process. One is the child, one is the parent. So here we have this fork library function. And if the library function returns 0, it means you are in the child. If otherwise, it's a parent. So in this program, you can say we run the fork. After the fork, 2 copies of program exactly the same will be in the system. However, one of them with a return value of 0, another one with a return value of something bigger. It's a PID of the child. So the child will print out its own PID by printf child PID this line, child PID and get PID. Actually, get PID is also a C library eventually called a system call called the get PID, because only kernel knows your PID's process ID. Then the child process will call valfoo. If valfoo returns, it print out IPD the foo, then exit. On the parent side, the parent will print out its own PID as well. And after that, it will just wait for its child. If its child returns, well, if the child finishes, the child obviously, the process doesn't exist anymore after it finishes because it calls exit. However, the parent still exists. The parent will go back to the beginning of the loop, then fork again. So this is why it's kind of like a web service. If you get an input, the web service may create a new process or thread and keep doing that. Then let's take a look at this valfoo function. So the valfoo function, first of all, it has a local variable, a buffer. After that, we have a file pointer. Then it also has a big while loop. In that loop, it tries to open a local file called exploit. It will only just read that exploit. If that file doesn't exist, it will just, it's actually a small while loop. If that file doesn't exist, it will try to do that again. So until it finds that file and open that file. After that, it will try to sleep a little bit. The reason I put a sleep here is just to synchronize, because we are going to write a lot of program to write to the local exploit file. Then there is a global variable. No, this is a, yeah, this is a global variable for the read. Then there is a memory set to set the buffer, the global buffer 200 bytes to 0. Then we are going to read from the exploit file. We're going to read at most 70 bytes here, actually. So the buffer is 200 bytes, and we are only reading 70 bytes. So there's no buffer overflow at this line. Okay. After this line, it prints out the child process, read so many bytes, and it's trying to guess what the canary is. It will print out a specific location of that exploit. That is the location of the canary. We will see why that is a location of the canary later. Then it will do a memory copy from that global variable to the local variable buffer. And this memory copy is where the buffer overflow may happen, because you can see the buffer here is 40 bytes. Of course, the distance between the buffer and say the EBP could be bigger than 40 bytes, but still, we can write at as big as 70 bytes, so still could overflow the return address, save the EBP, and everything there. So this is a vulnerable one. The reason I'm using memory copy instead of string copy here is I give you the ability to put zeros in your exploit. If I use a string copy or string uncopy, it will stop when it reaches a zero, find a zero, right? But I use memory copy, so for this one, it makes the job a little bit easier. You can have a zeros in your exploit. Then it will just close the program, close the file, remove the exploit, and then return. So if there is no buffer overflow, your buffer overflow is not successful, what will happen is this function will return normally, and it will print out I pity the fool. Okay. If there is a buffer overflow and detected by the stack cookie mechanism, then when this program returns, you will see the line printed out by the C library stack smashing detected. Okay, so that's the second case. So the third case, what you want to do is you want to successfully exploit this program, make it return you a shell, and it will not be detected. So to do that, what we always do is we just do, okay. What we always do, we can do an object dump. Here, but the right hand side, you have the val foo. And then let's see if we can find. So here is a memory set, and in the memory set we have how many? We have 3 arguments here. The first one is target, so this one enters the stack last. Then we have a global buffer. So basically, this is the buffer we want to overflow. So we can quickly check its address. It will be in AEX. Then in this case, its address is actually it's EBP. So this function is actually using EBP to address that. So it's EBP plus 9C. If we translate that to this one is EBX, sorry. So it will take some time to translate this into EBP one. But anyway, after the translation, what I show here is this is what the stack look like for this example. We have the buffer. The buffer is 40 bytes. However, the distance between the beginning of the buffer to the saved EBP is actually 52 bytes based on my calculation there. And we know there is a 4 bytes canary, and the canary is right after the buffer. So the buffer is exactly 40 bytes, then 4 bytes of canary. So after that, actually we still have 8 bytes of space between the canary and the saved EBP there. We'll have saved EBP when we'll have the return. So if we want to exploit this program to give us a shell, this program doesn't have that stack non-execution enabled, so we can execute on the stack. So that makes our job a little bit easier. We only need to bypass the generator. So what we can do is we are going to put a share code on the stack. We're using stack, we're using environment variable. We can put a large stack there. After that, we are going to override this whole thing. We are going to put something in the buffer. The value doesn't really matter. The content doesn't matter. Then we are going to override the canary here. This 4 bytes has to be accurate. If one byte is wrong, one bit is wrong, the program will just simply crash. After that, we can put 8 bytes of garbage here. We don't care. There are 8 bytes here. We don't care. Then we have a saved EBP value. We don't care. So 12 bytes of garbage. Then we put a return address to point to our share code set. That's what we are going to do here. So to do that, the first thing we want to do, let's see, I think my system right now, I have address space layout randomization enabled. Let's disable that. I think I have the share code already. Let's see, I have a get environment variable code. So let's say, I run this code, I get the share code address. I run it multiple times. You can see it has a different address. That's because I have address space layout randomization enabled, which we will talk about later, how to bypass that. So then let's first disable that to make things a little bit easier. So you can see in real world hacks, you have to combine all the techniques together because there are a lot of layers of defense and you need to bypass them one by one. In the class, we're just doing things in a more isolated way. We're not enabling all the defenses at the same time. Okay, so let's disable this. Okay, now I think we have it disabled. Let's see. Okay, let's see. Well, after we run it multiple times, we get the same address for the share code. So we have ASLR disabled. Next, what we are going to do is we already put the share code on the stack. I use this one, so it's 500 bytes of stack there. Then I'm going to show you my exploit. This is actually my code to generate the exploit. So here I have what the final exploit should look like. 40 bytes of garbage for buffer, right? Then 4 bytes of canary, 12 bytes of garbage, 8 is a room between saved EBP and canary and another 4 is the safety EBT within there. Then we have 4 bytes of return address. So this is a final exploit. It should look like this. Final exploit should look like this. However, we need to guess this 4 bytes. What we are going to do is to guess that we're going to send 40 bytes there. Now after 40 bytes, we will send 1 byte. And that 1 byte we are going to send from 0 to 255. So we're going to try 256 times. And for one of them, instead of showing us one of them, we don't know which. Okay, because the canary value will only be generated randomly when you start the program. We don't know which, but one of them, the first one is actually 0. We can see that. So we're talking about the second one here. So for one of which, instead of the terminal showing us stack smashing detected, it will return normally. It will show IPT the full. The program will not crash. We didn't override anything sensitive there yet. The program will not crash. It will just show us IPT the full. So let me change this script a little bit. So what I can do is, you can see in my, I'm not really a good Python developer anyway, but you can say there is a for loop. In the for loop, I have this number. Then I will write 4 bytes. Then this one, I will just, this one, let me get rid of this. Down here, this is at 1 byte. One byte we know it's always 0. Then we make B C1. Okay, looks correct. So that's our, we're guessing the second byte basically. The first byte is always 0. You know that. Now we go to the other folder, the other terminal. Where is the folder? Okay, we have that. Let's have the server, the program running. So now you can see we have this target program running. The target program has actually we have 2 processes running right now. One is the parent, one is the child. The child right now, what it's doing, the parent what it's doing is waiting for the child to exit. The child what it's doing is to keep reading the local folder, try to say if there is a file called exploit. Let's use say the say code here. It is trying to open the exploit. It's not really just a moving bit. So that's why what you see here is we have those 2 printout. So on the right hand terminal, what we are going to do is we are going to run our exploit Python code, which will keep generating exploit. Then if we run this, you can see the left hand side we start to receiving the exploit, and every time it says stack smashing detected. Okay. Let me know when you say IPT the full. That's when we guess that right. The program is a little bit slow because in my C code, I have that sleep state. It doesn't mean in general, the target program will always be this. So we already give 30, 40 something because this is a hex, not decimal. I don't know really what the calorie is. So we're actually guessing. I don't know what it is. So in some of our homework, especially the ones on servers like Maze, like Behemoth, the one we did before. Oh, we got it. Okay, you can see here, IPT the foods. So when that 1 byte is 49, the program didn't branch, the chart didn't branch. We do not be the food for a branch again. So what we can do is we change our script again. We know the second byte will be 49. Is it 49 here? Yeah, it's 49. Okay, it's 49. Good. Okay, we didn't really stop the server process. The server process is still running, the child process is still running. If we stop it, then we create again, we will have a different error, so we cannot stop it. Then our attack goes on, start receiving new ones. So this time we are guessing the third one. So a lot of real-time hacking involves guessing, because there is no way for you to find out the exact location or something. You always design, including that big lob select, that is to make your guessing much easier. Higher chance to break the win. So right now we get 24 hex. Any questions? We're waiting for the results here. Which one? Oh, this one? Oh, that's a return address. That's a 4-byte return address. We want to, that's a shellcode address. We're going to return to there, right? Mm-hmm. Yes, exactly. Yes. Eventually we will put the real address there. Oh, we got it. So now the third byte is 66. Okay, we're lucky today actually. The numbers are quite small. So 66. So sometimes you can get really lucky. I remember several years ago we were playing a embedded CTF for the eCTF organized by Meyer, and our job is to design a secure music player and hack each other's music player. There were teams from other universities. So one of the features of secure music player is the user has to log in, play music. To log in, then obviously you need some PIN or password. So while the teams we try to hack, they use a very good hash algorithm. What is the best algorithm? S script or B script one? Those things. Okay. Very difficult to hack anyway. So if we use Hashcat, or based on our calculation, it will take us like 100 days or something to hack that. Running on a GPU we get from Amazon Vault. So technically, there's no way we can hack it because if we run that Amazon Cloud for 100 days, we probably need to pay $1,000. However, there's a bug in their implementation. Um, there's like a off one bug, off one byte bug. So technically, suppose for example, if you have to hack like you have to guess 8 bytes, then because of bug, you only need to guess 7 bytes. But there are several bugs in there, several other bugs in their implementation. So we were able to guess hack the pin in just 10 hours, 10 or 12 hours on Amazon Cloud using GPU, and we only paid like $10 to use the AWS service to get that. So sometimes you feel the design is very secure, but it doesn't mean you cannot hack it because there are always also implementation issues as well. Okay, let's keep guessing the last byte. Okay, now we start from this fourth byte. Okay, this time it's a bit longer there. Okay, what? Still press one. It's only 67. Now we go back to our share code. We know last byte 67. Right? So that's basically our, we find the canary there, then we create our share code. Our share code will look like this. Okay. 40 bytes of garbage, 4 bytes of canary, another, okay. Okay, this cycle actually is really good. Plus 8 plus 40. And the value doesn't matter. Let's just put an ace there. So this one will be 12 bytes. Then after that, we just need the return address. We just need the share code address. And let's get out. To check our share code address using this. So our share code address is DAA3. Remember, this address, you cannot use this address because this address actually points to the string, the beginning of the string. The beginning of the string will be as code. So there will be 5, 6 bytes that are not really share code, just as the main as code there. So you need to add something. We have a 500 bytes of lobsnet there. So we can just choose some big number. DAAC. So this one is FF. DAAC. So we just use DA. Change the DD probably too big. DA FF. That should be enough. What would it be? Oh, this B. This B means this is binary from binary. So that's Python syntax. Now we save this. Then let's try again. So if we get a shell. Yeah, it works. We got a shell. Got a shell here. So this is how we bypass the same cookies. Obviously, this approach works for 34 bits as well. Same technique, just that you need to guess longer. You have 7 bytes to guess. Here we only have 3 bytes to guess. Okay, let's keep moving. So homework this week is I will give you the target program, and you are going to develop your own exploit generator to generate an exploit. Obviously, you can see that you can write a more elegant code than I did there. My code I manually change that byte by byte, right? You can have another loop, so you don't need to manually change it. But here the key is you have to guess the cookies byte by byte. You cannot guess them at the same time. That would be too many. The big number is too big. I don't know how long you will spend to crank the program to do that way. So next we will talk about address space randomization. So this is another technique we have been avoiding talking about and touching so far in this class. All the hacks we did so far, we disabled this. This is a very useful defense, but all those defenses are indirect defense. They are not guaranteed to work. They only make hacking a little bit harder. So this ASLR has been deployed in modern operating systems. So all our modern operating systems will have this feature. No matter your laptop, your phone, your tablets, they all have this feature. However, the low-end devices we use in our lab usually they do not have those features. That's why one of our research directions is thinking about how do we enable this on those very low-end device, like your Nest controller, your phones, your Fitbits, those devices. How do we enable this feature there? ASLR works by randomization addresses of a process so that the attacker cannot know their exact location. A little bit history here. Back in 2001, the Linux Hacks project, I think it was a company working on that project. I don't know if that it's called CS Security or something. I don't know if that company still exists. So that company, they coined the term ASLR. They published their first design and the implementation back in 2001, a patch for the Linux kernel. Then the first mainstream operating system to support this was the OpenBSD back in 2003. Then Linux followed that in 2005. But of course, that time we're still mainly talking about ASLR for applications or user space ASLR. So if you create a new process, like you type LL, there's a new LL process. That LL every time will have a different address, but not really for the kernel. So every time you boot your system, the kernel always have the same address. Microsoft started offering kernel and user space ASR in Windows back in 2007. So all the current kernel ASR or KASR, there's a one-time randomization when the system boots. Okay, just once. So if your system stays no reboot forever, it's not that secure. Both Android, iOS support ASLR in 2011. That's actually 3 years after the first iPhone came out. 2012, OS X, iOS started supported kernel space ASLR. Linux also started supporting kernel space ASR back in 2014. So most of the system we're using, they have this feature. That's why every time we do hacking, we disable that. But like I said, it's not supported in embedded systems. And it will be very challenging to support those in embedded systems. First of all, since it's randomization, the key here is the entropy. The entropy has to be hard. The randomization doesn't really stop the attack. It just makes the attack harder. To make the attack harder, you just you need the attackers to guess so many times, right? So the entropy has to be huge. And to enable that, we have a MMU, and the MMU enables a huge address space. But for a lot of embedded devices, the address space is small. So no matter how much you random there, you can easily guess. Even for user space on current computers, you can say sometimes it's easy to guess. We're going to say that later in my example. So let's see how this user space ASLR works. So in the stack-based buffer overflow and also return to libc attacks, you need to jump to the share code on the stack or return to the libc function, for example, the system function. So either way, you have to know the target address you want to jump to. In the share code one, it's easier. It's easier for you because you can have a huge lob slab there. However, if you are doing the return to libc, you have to know the exact address for that system function. We have been doing that using GDB to justify that. But if you are an attacker, the attacker remote server, obviously you cannot run GDB on their machine to get the address. You have to guess. So the idea of ASLR to at least slow down this attack is to load the libraries, binaries to different address. So in other words, the defenders, they can change the layout of the process. So the defenders can put the libraries, functions, strings, even strings, at different locations every time we run the program. As a result, it's much harder for the attackers to know those addresses. So it's difficult for them to exploit those bugs, even if those bugs exist. A lot of background knowledge important for ASLR is something called position independent code, or position independent executables. It's called PIC or PIE. So if a piece of code is PIC, it means this piece of code can execute properly, regardless of its absolute address. It's the same piece of code, you put it in address 0, it runs. If you put it in address 5000, it still runs. Okay? So which means some of the instructions you need to carefully design. Of course, I mean, you think that most instructions, they can run anywhere, regardless where it is. For example, if you just add two registers together, you have and R1 and R2, it doesn't really matter where that instruction is. It always runs correctly. But some instructions, they will reference the memory, and that reference memory is based on other registers, and it's getting really complicated. So if you remember this picture from the first class, we said this is in general the address space of Linux process. It looks like this. We have the text segments, data segments, uninitialized global variables. Then we have heap goes up. We have those libraries, like C libraries in the memory mapped segments. Then on top of that, we have the stack, which goes up. Of course, I mean, you could have multiple threads, and there are multiple stacks. Then the higher 1 GB of memory, 32-bit, then we have the kernel. So this is what usually without the ASLR, this is what the space look like. So for traditional static program, when the process is created, the kernel will always bring the dot text and dot data from the executable to a fixed location in the virtual address space. Here, obviously, we're all talking about virtual address space. We don't care about physical address space. So because this is a static linked program, the libraries you are using are also in the .text section. There is no need to copy that BSS section because it should, for C code, that should be initialized to 0 at runtime at launch time. Then the bottom of the stack, which is high address, is also initialized at a fixed location. So if we have a static program with a shared library, static means not moving in this case, then but this program is dynamically linked, then it may have libraries. It may share libraries like libc with other process. Even though there is just one physical copy of libc in the physical memory, all the programs using it will map it to different location in their own virtual address space. However, without ASLR, that they were still mapped to the same location in their virtual address space. So the idea, also the text, other things will be, every time you run this program, it will be loaded to the same address. The idea of ASLR is very simple. We just randomize the location. Every time we load it into a different location. But to do that, obviously, the code must be able to run at different locations. Okay, so I have several examples here. I cannot get out. Oh, that's because I'm still sending things here. Okay, I was keep sending on the other side. Oops. Now I get out. Okay. So let's go to so we have this program. So when we run this program, it is just this is the program doesn't really doesn't do anything fancy. You can see that it were just a print out. It were just print out things in its address space. You will first print out the address of the printf, where the function is, the address of memory copy, where the function is, the distance between printf and the memory copy, Then the address of the system and the distance between those functions. Those are libc functions. After that, we print out the module functions, which is functions you develop as a programmer. From the main function, add function, the distance between them, the sub function, compute function, just print out the distance between them, and also print out the distance between the module functions and also the libc functions. After that, we have global variables address, the distance between them, the distance between functions, between them and the functions, and also global uninitialized variables. So those one goes to the data section, those one goes to the access section. So also this one will call local function, and you will print out the local functions address. So there's an function and a sub function. Just about the local variables. So when we run this program, so right now we don't have a ASLR enabled. When we run this program, we can run this. Let's run it multiple times. So right now we do not have the ASLR enabled. We run this program twice in two terminals, and you can say they have the exactly same address for everything. The printf always has address, so all the addresses are the same. Okay. So now let's enable address space layout randomization. Say what? Now we have it enabled, then we are going to run it here. And you can see the address are different. So this was the old one, this is the one we just run. So we can run another one on the left-hand side. Okay. So now we have two versions of this program running after enable ASLR. You can see they have different address. Printf has different address. Memory copy has different address. However, the distance between printf and memory copy, that stays the same, right? That tells you printf and memory copy, both of them are in one big block, and that block is not randomized inside. So that block is moved to some place. The system function the same, there's the same libc block. There could be several libc block or pages. After that, we have main function. And that's different address. But you also notice that the last, at least here I say the last three letters. Last three letters will be 12 bits. Those 12 bits are not changed. Could be a little bit more than 12 bits. In here, it's actually 16 bits. Right? So this one under the C314 or 40. This one's 8000. Here it's 18. C340. So and also the higher address is also at 7. So this one actually not just the change from 2C and 2 to B. Okay. So some looks like it's only probably several bits of randomness. So since it's only several bits, it's probably easy to guess. Then let's say the main functions where we said the distance between main and end is d0. they're the same as T0. However, let's say the distance between main and printf, main and printf. And this one is a module function, this is a libc function. You can see the distance, this one's changed. Okay. So those two blocks, the module block and the libc block, they were placed at different addresses independently. They are not associated with each other. So the distance between them changed. The global variables, the distance stay the same between two global variables, or even global variable between global variable and the main function will stay the same. Okay? So looks like .txt section and .data section, they have a fixed distance. However, their distance with libc can be randomized. The global variable here, yeah, those are different inputs. Those two are those global variables. Okay. K is initialized, L is non-initialized. So the BSS is not at the same address. When we have local variables which are stacked, or they say they're also right from that. You can say every time you run the program, you run it again, you get another different address. You can also do another, I think it's LDD or LRT. LDD. So LDD tells you if you run this program, where the libraries were loaded to. And if you run this multiple times, you can see the library will be loaded to different ends. We run it twice. The first one goes to line the second one it goes to. Oh, this one much different. Okay, so they're different ends. So that is how address-based auto randomization works. What's the question? Okay. So we can also use another tool I put here. Checksec. You can use the checksec on a binary to say what security features. So this tool. This tool tells you what security features are enabled in this binary. For example, there's no canary for this one. Stack, non-execution is enabled. PIE, provision, independent code is enabled. RPass, I'm not sure about those two are unpass. Those two, it's also relocation. Reload. So that one is related to the PIE. You mean, what do you mean by shell script? Okay. Yeah, this is not a command. This is just a tool. Yeah, it's a tool. It's not a built-in command. Here we can also say use NM. We'll be using this tool to say the symbols in a binary. As you can see, all the symbols, those are PIE compiler code. As you can see, those symbols, obviously, those are not absolute address. You start with zeros, right? That makes sense. Absolute address doesn't start with zero. Even for the 64-bit version, start with zero. So those are just offset. They're not really the absolute address. The absolute address is only determined after this program is the process is created. And there are different symbols here. For example, some of them are uppercase, some of them are lowercase. We can say T. T obviously is text. If it's uppercase, means it's external. If it's a lowercase t, it's internal. This is similar to the same concept of external and internal symbols. Then there are E or spanner, also other things. U is undefined. They are undefined because those are libc functions. If your program is dynamically linked, the libc function memory copy is not in your program. Only after your program is loaded in the process, the loader will resolve this address, so the program knows where the function is. That's related to the GOT and the PRT we talked earlier in this class. So because of this PIE thing, one interesting thing is we see a lot of this get PC func AX, get PC func, EX, those function calls. Those function calls are just to get the EAX or AX value at runtime. The reason we want to do that is you can see this one, 2BDF. This is a immediate number. So this is hard coded. This is what compiler generates, that number. Then we add AES to this. So the AES looks like a base address, which can only determine at runtime. And the system, the OS will feed you that address, and you can get that base address by calling the function. And this 2BDF is obviously an offset. And that offset is probably for some, in this case, let's say, where are we using AEX here? EX. Let's say EX here. No, we're not using EX. Here, right? This is 2-bit. So until here we're using AEX. So this is the address. I'm not sure. In this case, here we're using EX. So the printf will use the format string as input. And that format string's address of push down stack, so it's in EDX. However, that format string is not always at a fixed location. That's why we need to runtime, we need to calculate the value of EDX, and that is where EAX points to minus this fixed number, and EAX is also computed at runtime. Right? So that's why even if so printf, we just print out a string, but that string is not at a fixed location. That's why the compiler cannot hard code this in the machine code. So it has all those instructions to get the address at runtime. So PIE is actually quite efficient. Only 1%, less than 1% overhead in 64-bit version. Also because the 64-bit version, you can directly address RIP. 32-bit, you cannot use this register or EIP directly. So because of this, what we can do is we can always put, let's say if this address has some data, RIP plus this 23423 has some data you want to use. As long as you put that data always at the same distance as your code, whenever you randomize them together. So this line of instruction will work, right? And it's quite fast. However, for 32-bit, because you don't have this, you have to call this function, those functions. There are a lot of registers you can use here. Then the overhead is like 3%. To disable or enable ASLR on Ubuntu, you can just use those two commands. We already compared those. Okay, how do we bypass this? The idea is the same. To bypass any mechanism that use randomization, you just need to guess and find a smart way to guess. Then it's a number game. You hope the number you need, the times you need to get is smaller than the attackers, the defenders' entropy. So in real world, even though in theory those approaches work well, or in theory they do not always work, but if the entropy is big, they work well. But you need to pay attention to implementation issues, and those implementation issues could significantly reduce the entropy of their implementation to make your tank much easier. Okay, let's say another example here. So for this example, we are going to, this is the first time we exploit a program with ASLR enabled. Very simple program, main function called the vulnerable function. The vulnerable function will print out its own address first to make your job easier. Then there is a local buffer, 8 bytes in C. Then you get the input from stdin. Then you check how big that buffer is. Then the goal here is to overflow this function and call when this one returns. Instead of return to main function, we return to print secret. Right? This is similar to our very first buffer overflow return address example. The only difference is right now we have ASLR enabled. So we do not know the exact address of print secret. Previously we know it. Okay. So how do we do this? Like we approach all other programs, let's first do an object dump to figure out how many bytes we need to overwrite. This is our vol foo, and the vulnerable function is this read. This read related down to EBP -10. So because we're reading from stdin, so the gets actually when compiled it becomes free. It's not actually gets anymore. So the first one is the fire descriptor. stdin is fire descriptor is 0. That's why we're pushing 0 to the stack here. Then we have the buffer we want to store there, which is EBP -10. So actually the 16 bytes. So to override this one, we need 16 bytes. Then we can say the vol foo's location is 1240. 1240. Printf is 12.e. Those are their relative address anyway. The main function is 12ec. After this vol foo, you reduce 1285, right? That's where it should return to. So how do we return to print f secret? We don't have the exact address. The exact address at runtime will be 4 bytes. We don't know the value of the higher several bytes, maybe 3 bytes. So this one may add a base here to make this something bigger, not for everyone. It's much easier than they think here. So this is an easy hack. Okay, let's see if we can figure this out. It's a very easy hack. What? Some distance, okay? That's a good thinking on top. What? We have the wall for some campus, or do we got it? We're not going to divide it. Okay, we're not going to divide it. Yeah, there's a thing. So what is the yeah. So like I said before, those functions, they will be randomized together, right? So even if they have a different, those functions have different address, but their higher bytes of those addresses will be the same. We don't know the value of their high bytes because every time it's randomized, but we know they will be the same, right? Which one? No, the lower, the lower bit is this one. E0, they're not the same, right? But the higher bits, they will be the higher bytes will be the same, right? So exactly, that's what we're going to do. We're not going to override 4 bytes. The correct address is already there for us, actually, right? Because when you do this main function, you call the bubble, this address, at runtime, we don't know what this address of the instruction is, but that address will be considered to stack. We only need to change the last byte of this to point to print sequence. So in this case, the main function, this one is 12A5. And this one is 12OD. So we only need to change this to 12OD. So let's say it works. So this one takes 16 bytes of garbage, right? No, 20 bytes of garbage. 20 bytes of garbage. Then just OD there, right? Then we give this to this. Does it work? Read. Let's see. That's 12OD there. 20 bucks. So both this address. Oh, this one may be okay. This one we may have a canary there. That might be a problem. Oops. Let's see if we have the same cookie there. No, this one. Maybe that's a problem. No, this one doesn't have cookies. Did we calculate it wrong? It was 10. 10 is 16. 4 bytes is 20. Okay, we can debug this one. See what's going on. What is the syntax again? $3? Oh, like this. $1. Python say print a 20 plus 0D 0D. Okay. Now we are in lawful. Just going. Skip that. We're going to call printf. This is not the vulnerable one, so here. Skip. Now we're going to do read. So before we do read, let's check the stack. Okay, then 1 bytes, 4 bytes. Of EBP minus 10. So that's where our buffer is. So there will be 16 bytes of garbage. Then another bytes. This is saved EBP. Then this one is a return address 5655. So this is in the main function address. So this is the return address. So we're only going to return this one. No, let's see if print secret is here. Print secret. Okay, so print secret is 565562 OD. Okay, so if we only overwrite this one, it should work. Let's see why it was not working. So after we call this, then we examine the stack again. Where am I? Okay. Let's do one more. Now should be able to get this. Oh, why we're getting to? Because we. It's weird. We didn't change the EBP. So right now we have C418 previous address. The previous address was also C418. This is actually correct. Oh, yeah, it's correct. It's ace, right? We put 28 there. Then this one they will consider that as a string, but it's actually on the line 300. So this one is actually correct. So keep going. We move this. Oh, this makes sense. Do it again. And let's see, where do we return? We are returning to, we're returning to here. 0, A, D, 0. Yes, that's correct. Is that correct? No, there are several bytes off. Oh, this one is OA, but here is 62. Oh, so in this example, actually are 2 bytes. We need to change 2 bytes. But how do we know? Oh, so remember that off, that base, no, not base, the offset. Let me go to the next terminal. Here. OBJ dump. Okay. So you can see all the offsets for the address started with 12. And now when we actually run the program, it becomes 62. So the base address is like the last 2 bytes of the base address is like 5,000 next. So that 5,000 added to here, you get this. Right? So how do we get that? Yeah, that's different than address. Let's see where's name.
those was right. Oh, that's I know why it's OA now. That O0A was a new line. That's OA. That's a new line. That's because that's why we'll actually override 2 lines. Wait, so we handle this one.
What was the command we used in the beginning? This one. What? Okay, yeah. Yeah. What we can do is similar. We can do this to let's say 1.txt. Then we do xxc to say we have that new line sign and run. We do have the new line sign and run. We have to have 0A along that. So you say we can do echo. So how do we get rid of that in Python? What? Yes, but the previous one we are using, we don't have this. I think I'm missing something here. What is the flag we should use to not different? OA and but when I do echo minus I do echo so I do this myself, then like this, okay, like this. Okay, let's see. Yeah, it works. Okay, so this thing we direct it to here. Okay, so that's all. That's all in secret. This is the secret. Yeah, that's because we have the OA here. That's why whenever you find out you a condition like this, you find your exploit is not working. The key is just to try to understand the example memory, example code to say what's wrong. It could be just 1 byte that ruins everything. Then you think about how we fix it. Okay, let's keep moving. What's the time? Let's take a 5-minute break, I guess. We will come back 6:32. Which one is it? Maze 2? I didn't prepare that. Let's do it maybe after the midterm, 2 weeks from now. So, yeah, just remind me before the class.
Okay.
Yeah.
You didn't prepare for that?
Well, we can do it. I mean,
No, it's still in the same one part.
Okay.
The
let me check what's the password. Let's log in there to take a look.
password is FOOT.
Hold on, let me go to my website to find that password, and I just want to copy the command. That's why.
Okay.
And let's say, where is it? Oh, it's not on my site. It's on the homework. Homework. Okay. So, what's your password?
Password's on the slides.
Ah, Jesus.
It's like I know what it is. FOOTHAT.
If it's on the site, okay. What's that?
FOOG.
G. Okay, good. Okay, let's see. Can I copy?
last question more. Yeah, I just don't understand like
Okay, where's the correct base?
right? Yeah.
So we are doing maze 2.
Maze 2, yeah.
Okay, so let's try to arbitrary down the maze 2. So which one is the only main function?
Only main function, yeah.
Okay, I don't remember which one.
Okay.
Okay, let's see. So there is a string of uncopy, and you only copy 8 bytes, right?
Right, yeah.
Okay, you were copied to EBP minus C, which is 12 bytes.
Right.
So you're not going to overwrite anything critical there.
Right.
However, EBP. Okay. So EBP minus C, then you are overwriting. So then EBP minus 4, move EBP minus 4 to EIX.
Mhm.
Then what is EBP minus 4? This is this, but this is not something you changed, right? So
No,
it was
no,
already there.
It was already there. So there's
So-
a call to EAX before
Yeah.
return.
Then must
Yeah, that's it. We just need to
so
yeah, like you put the address of like the environment. No. No, there's a start. So what you're inputting is just like a sample code. Yeah, that's what I didn't understand. Like, how do you put the assembly code? I know you gave us the right.
yeah, I give you guys a link. So let's say where's the link?
So
To
the
the
homework.
homework. Oops. What's so stupid? Okay, fine.
You can just Google. You're the first one you do it.
Okay. Google something online.
The first one is
So let's say, for example, you want to. So how do you want to do it? You want to just jump to your share code?
Yeah.
Jump to a fixed location, something like that. That's what I'm
the
talking about.
shellcode is an environment variable, right?
Yes. Yeah.
That's
Something like this.
that's a trap. Right. Well, first you're right, argc, right? So you cannot directly jump to the.
So when you when you do this, you are not really jumping to this location. This it will be used. This instruction doesn't mean jump to this location. Basically,
Okay.
it means use this as an offset, right? That's the meaning of this.
Okay.
Yeah. So that's
Is
why.
this only for x86.
Well,
or
each
does-
platform is different, I would say. But so if you go to, let's say, jump x86.
I think I read that x86 64 does allow
You can see whatever you put there is relative. So then if you go back to here, oops. If you jump to here, this one we have E901, right? E901 is actually it's not here. It's not really here, but
Okay, so you translate. I mean, you put that assembly code there, but
Mhm.
then you place this in EAX or like, where do you like overwrite?
yeah, you can do some anyway. So this one probably will be interpreted as a lective number. So you will jump to the curve relative to current address will be a lower address
Mhm.
because this is the FF, two complementary there. Then what you can do is you will probably can move this one to EAX. So you can
And there's already a code.
jump EAX, something like this.
There's other approach like calculating the difference between I guess the difference using that difference as
Well, it works.
I didn't try that.
It works.
It just came up now. Yeah. I try to use the J equal.
Yeah.
But you need a comparison before that. Yeah, so it doesn't work.
What you described there obviously will work, but it's much more job for you. You need to find out where the current location.
Yeah, that's why I didn't try that.
It will work. Yeah.
So this is more than 4 bytes.
We can write up to 8 bytes. Yeah, this is exactly 7 bytes.
Just 7 bytes.
That's why it's doable.
Oh.
Yeah.
Okay.
And also, I mean, you know, let's say if the EAX already have the same, like the higher 2 bytes already have the value you want, then you can just move to AL instead of move to EAX, right?
Yeah.
Those are the tricks when you write a share code to make the share code a little bit smaller. Yeah.
Okay.
Yeah, you find out what is already in there. Yeah. So basically that's how it works.
Is there any way to
I cannot promise. I haven't worked on it yet.
I was gonna ask about the bonus from like 2 weeks ago. That was gonna be on the
Which one is it?
it?
Bonus? Oh, that one. Probably not.
Okay, yeah.
Yeah.
That one was a little difficult.
Yeah. Okay.
Okay, welcome back. Let's say. So, if you want to know more about ASLR, I suggest you read this paper published in NDSS 2016. So NDSS is one of our top conferences. There are 4. This is one of them, and so many very influential system security papers came out of this conference. Even though the name of this conference is Network Security, or System Security papers came. So one of the limitations of deployed ASLR, just we saw that, is it is a one-time randomization when you launch the program, or for the kernel, it's a one-time when you boot the kernel. So same as the stack cookies, which will not be regenerated when a new process is created. So the memory layout of a child, another issue is the memory layout of the child process will not be re-randomized when the parent program is forked. So you can say the similar attack, how we attack the stack cookies, would be used here to attack ASLR as well. And this paper, published 5-6 years ago, was trying to handle this problem. The child process, after this paper, what they propose there is to re-randomize the child process address space. This is all what they propose. However, this problem is actually very difficult. I don't believe the approach they propose here is perfect. They only prove it works empirically on some programs, but I feel it's not guaranteed it can work on all the programs. So quite difficult problem. Okay. So the next, we've been talking about several defensive solutions, and the next one, well, we will talk about another one for secure computing mode, or SecComp. So this is actually a kernel system call firewall. This is just a firewall. The kernel will decide if a program can make certain system calls. So imagine your program. So this is kind of like a least privilege, trying to achieve least privilege for different programs. We have seen so many programs, and those programs will do some very simple tasks. There is no reason those programs should be able to call some dangerous system calls. You should not call exe, you should not call fork, right? Because when you do a program, you already know
what the program will do. It doesn't really need those. If you consider calling those system calls of privilege or a permission, your program doesn't need that. And this feature provided by Linux kernel. I don't remember this when we restart. So this is kind of like have a firewall. It tells the kernel at the very beginning when the program runs, because those other permitted system call from this program. Even if the program is exploited later, this program will not be able to call execve. Even if there is a buffer overflow, if you cannot call execve, it cannot call your generate. You cannot run your shellcode. It will not make any damage there. So the syntax of this tool can allow certain system calls, can disable system calls, and also filter allowed or disallowed system calls based on arguments. And those rules are inherited by children. Some history here, 2005, the first design, and very quickly it was merged into Linux kernel. Then Android also has this feature since 2017. Let's take a simple, let's take a look at a simple example here. Okay, so this is our program that wants to use this feature. So this could be a program you develop, and you think my program may have vulnerability, but even if it's exploited, it's not very much damage. So what you can do is you can basically you first initialize this library. We just add a rule here, and the rule says that if this program makes an execve system call, then this program should be killed. That's it. Then if we, after that, if we execute this new enhancing, then we will just crash. So I'm going to show you. I think I have one. Oops. So we're going to compile this as allow and disallow. Disallow. Okay. So now we have both of them. The difference is in one of them defined. So the disallow, this part will be compiled. The allow one, this part will not be compiled. So allow one will only have this. So the allow one, if we run this program, will be sec allow. We run this program, obviously we're just a cat, the secret. It should be able to give us a secret, which is just a random string in the file. So if we do disallow one, you can say, because we're trying to make a system call here, the execve system call, and the system will not say this is an invalid system call. So this is one way to protect your own program. Okay, let's keep moving. So that is the stack-based buffer overflow differences we're going to talk about. Next, we're going to do something fun today. We're going to write some shellcode in class. Right now, all of us have been using one, maybe two shellcode, not just one shellcode, right?
We just, or every time we write that shellcode, we use the same shellcode. We understand how it works, but we never write our shellcode. Today we are going to develop some shellcode, and the shellcode first is most likely you don't want zeros in your shellcode because a lot of the multiple functions there's they start at 0. Then there are shellcode. There are just alphanumerical characters. There are even English shellcode. So there's a old book, the Shellcoder's Handbook. You probably can get this for $3-4 on Amazon because it's really old, 20 years old maybe. So on this book, they talk about how to develop shellcode for different architecture. So the idea is different architecture, but the idea will be the same. Yeah, just making different system calls. So you can learn what system calls are available on the architecture. You need to write several lines of assembly code. So this is a shellcode tester I provide. This is a very simple program. I will just do a memory map at the beginning to create one. This one should be the size of this like 1 page. So we create 1 page for you. Then I just read from stdin to that page. Then I will just call that. So you just need to put your shellcode to the stdin. So this is going to execute the shellcode. So in the homework, you are going to do something a little bit more challenging. You are going to develop shellcode without zeros. You're going to develop shellcode with only alphanumerical characters. And to do that, I will change the tester a little bit. So I will make sure after we read this, I will get rid of those zeros. I will get rid of the other non-readable characters. So I can show you where the shellcode one tester. For example, this is a tester program. So we have tester ASCII. Let's see. So this program, where instead of doing a copy, I will do an ASCII copy. So I will only copy the ASCII characters in your shellcode to the buffer and codec. So if you have non-ASCII characters there, your shellcode will not work. Okay. So basically, this is use the online tool I showed you here to try different instructions and to make sure it not generate something you don't want. For example, here, this instruction, those two instructions, because you have a zero, because you have a zero, the shellcode eventually generates will have a 0, 0, right? We need to find a way to remove that zero and make the shellcode work. More challenging is you need to find the ASCII characters or English. We're not doing English because. Okay, so before we start working on this, let me remind you something. To invoke a system call on x86, 32-bit, we put the system call number in EAX, then we put the other arguments in EBX, ECX, EDX, and other things. Then you just need to run an int 80 in hex. That's a shellcode. That's a system call. Then you put the return value back in EAX. The system will put the return value back in EAX. And sometimes you probably need to make several system calls. So far, the shellcode we're using makes two system calls. The first one is exe7e, the second one is exit. We're not really using the second one. But what if the goal of your shellcode is not to return a shell? Instead, we're going to read a file. There is a secret file in the file system. We're going to read it. So what should our shellcode do? This is the same as you program in C. How do you do that? When you program in C or Python, the first step to read a file is to open that file, right? Open that file, you get a file descriptor. Then you use read to do that. So there is a system call for open. There is also a system call for read. Then after that, you probably want to output it to the terminal. So there is another system call for write. And the file descriptor for them is just to use write. You need to use it's just a one of the system because one is a std out. Std in is 0, std out is 1. So if you want to do EVE, CVE, then this is how you're going to do it. We already saw this. If you want to create a string, what you can do is you can just push those there. Of course, here I have a push 0. If you want to get rid of 0, you just do x or EAX and EAX, then push EAX. It will get the same thing. Okay, so let's try to say, I think I want ask you guys to do. Let's do this one. I will send you several helper tools on Slack, including Makefile, something like that. Let me show you how it works first. So in this folder, what we have is I have a Makefile. Let's take a look at Makefile. The Makefile will compile all kinds of tools here for you, and also, this one is not compiling shellcode. I need to give you another. Makefile here. So this, I give you a template. Let's take a look at the template. Okay, so this is this can be a template for you to start with. But your goal is to write a shellcode. Our around to help you to write a shellcode to open a local file. You can create any file on your local system. Obviously, if your name is simple, just one character will be easier for you. Then you open that file, read that file, and print out that file to the terminal. That is what your shellcode will do. There is no restrictions on your shellcode for this one. Your shellcode can have zeros. We will just use 32-bit zero tester to test it. Let's say, for example, now here we have a shellcode, right? After we compare it, we already got that shellcode 32 raw. Then we can just pipe this into the tester 32.0. And this one's not working. Here's segment 4 here. Just so many zeros here. Okay, maybe the shellcode I put here doesn't make sense. This is just a template anyway.
Where is the command that one people going to use to compile? Oh yeah, so those are the commands you want to use to compile. So you are going to code, not this one, that's the 2 You're going to code a file like this, then use those commands to compile it. The first one is GCC, you use GCC to compile it. Then use obj copy to dump the text section. Yes. Okay, let me move those to the stack. Is everyone on stack one? Okay, I send you. I send you the tester, which is the program to enable you to run your shellcode, and also a template for shellcode, and also those two commands to compile this shellcode. Or those two first let's do open.
So I just send you another link, which has all the system call numbers and what arguments you should fill out.
Anyone get it working? Just open? No? No. Let me show you guys. Okay, so this is a share code I just wrote, so it's only 690. So from this table, okay, from this table, there is no system for open. We will make system for open. We need to move 5 to either X, move the address of the name of the file over there. Then the other two flag and no boundary matter, you can just put it over there. We don't want the input go wrong. Then this is what I did there. I just move 5 to EX. Then I push this value there. This is just a 414141. There will be 3 A's, uppercase 3 A's. Because in this case, I didn't say what file name should be for anything. So let me show you this.
what I did there was,
Okay, I just want to put a 414 point there, and I get a decimal number. Well, you can do text. I don't remember the syntax, so I change the decimal. So that's a number I have. Then I push this to stack. I push this to stack. So after I push this is actually 4 bytes, okay, not 3 bytes. 0, 0, 4, 1, 4, 1, 4. The higher byte is 2 zeros, is the 0 bytes, right? When I push this to stack, which means on stack, there will be a string. The string will be 3 8s, uppercase. Then that's a firing I want. Then where is that string? It's ESP, because I just push it. ESP. Then move ESP to EBP. Then I'm done. That's all we need. Then the other two just move to there to make this EA. So how do we know it is working? We can just debug. So this one is not going to show anything. So we just debug this one. Debug it. I set a breakpoint in main. Then I run this. I use those commands, compile this, and generate the shellcode. Those two commands. The first one is 268. The second one is obj copy. Then we just do it here. Then we are in our main function. At some point, you will see it's calling our shellcode using call EAX. Here you can say call EAX. That is after you read the file and going to give the control to our shellcode. So here we do SI instead of NI. So we do SI. Then now we are in our shellcode. Well, this is inheritance. When we write it with ATMP syntax. If you prefer inter syntax, you can just you can use inter syntax. There's a line in the template says this is ATMP syntax. You can remove that. So after that, we just do it step by step. So this int 80, this is the system call. After the system call, the return in EAX should give us the file descriptor. All right. So if we do this, then we check the value of EAX. Right now, the EAX value is 5. That's a system call number. After we do this, we get the file descriptor number 3. So we know that's correct. 0 is for std in. 1 is for std out. 2 is for std error. That's why that's the next available file descriptor number for us. That's why we get 3. Okay. So if let's say we remove the file, so I created a file AAA here. Let's just remove it. We remove the file. The file is not here anymore. We do the same thing. We debug the main. We run it, the same shellcode. Keep doing it until we have that for EAX. Read EAX. Okay, now we are in our shellcode. We do the same thing. Now we're going to make the system call. Pay attention to the EAX. That's our return. See, that's a negative number, right? And that negative number basically tells us what is the error code. So maybe you can check. Let's say how do we? Let's say we can do mux error code. Oh yeah, maybe we can just we do that. Not sure. Those numbers are solid numbers. Actually, let me see. So this is E, and so FE. So this is -2. So let's search Linux error -2. I think -22. Not sure. Maybe it should be 2. Let's do arrow number 2. Which one? What? This one? Arrow 2. Oh yeah, it's actually so arrow number 2 is no such file or directory. That's basically what we get when we make the system call. But what you really get in the register is the minus number, is the negative number -2. So that is how to open the file. Then after open the file, next step is to read the file. And then now you have the file descriptor. The file descriptor is in EAX, right? When you have the file, then you make the next step is to make the read system call. And you will use this read. Then you need a buffer. Then you need how many bytes you want to read. Okay, let's do 5 more minutes. And the password will be dismissed. So how many of you are using N1 CPU? One, two, three. What are you using N1? Okay, you guys use all laptop, so yeah. It's not going to work. You can use the on the machine.
Actually, I forgot to mention that I think there's a easy version of this to solve this problem. After we open, we don't have to do read and write. Because when you read and write, we need to do have a buffer to store whatever you read, then write. I think I remember there's another system called some file or something. Let's check. I think it's some file. Yeah, see, this is number 2. So this is the system. So we can just use this system call. It's called send file. And when using the send file, you don't need to worry about the buffer. So first you open, you get the file descriptor longer story. Then you do a send file, the out will be 1. The in will be 3. When the offset is the 0 times it's only box. So don't need to put a buffer in the address space. This is the easy version. Okay, any questions? Okay, so 5:50, you're free to go. And next week, we are to have the exam. You're not going to write shape for your exam. But bring on computer, come early, We will have 2 hours again. Good luck next week.